The broadcast is now starting. All attendees are in listen-only mode.
Hi, it's Michael Walton from Brigel Medical, and this is the second part of our presentations on electrical safety. This is a presentation that's working with our partners, Oregon Healthcare. I'm going to go through what we did in the first part, and then we'll go straight into the second part of this presentation. So the first part, we were working with we discussed safe working practices that went into electric shock, the physiological effects of current, the body model of 60601, and the frequency response of human. We spoke about leakage current, we spoke about TN systems, secondary earth paths. We spoke a little about risk assessment and ISO 14971 and some quality management systems. We also spoke, or Dinesh spoke about the NABH, which is the National Accreditation Board for Hospitals and Healthcare Providers, which give an accreditation for the calibration of medical devices. That presentation is available. We will link it in the email that you'll get sent as part of this second presentation. So I'll go straight into the second presentation. Standards and code. What's the difference between a code and a standard? A standard is a document containing technical definitions, procedures, guidance for manufacturers, installers, and equipment users, and it contains mandatory requirements for compliance, but can be voluntary. A code is a document that is enacted into law, either local, regional, or national authorities, having the jurisdiction so that an engineer or contractor is legally obliged to comply, containing mandatory requirements in compliance with law. So a code of practice and a standard are very different, but they still have quality management systems at heart. Standards are to adhere to IEC standards is adhering to best practice. So from a working point of view, it is a good thing to get into standards and to adhere to them and do your safety testing to international standards. I'm going to go straight into 60601. 60601 is mandatory design and type test standard for medical devices, electrical, mechanical safety and compliance of medical electronic equipment to ensure safety of the patient, the user, and the environment. And it was first published in 1977. The body model, which we discussed in the first part of this series, is a simulation of how the body responds to leakage current or current. And we can see from the x-axis, as frequency is increased, then we're not interested in this frequency. Effectively, we have a low-pass filter. We're only really interested in this frequency range which is more responsive and more stimulated. A human is more stimulated when an electrical current could be applied to a human in a macro or micro shock instance. 60601 has various fault conditions. We have an open earth, we have reverse mains, we have open neutral, and we have mains on applied pot. We also have mains on signal input or signal output, usually using the acronym SIPSOP. This test is not generally required as part of your planned performance maintenance, but it can be used in acceptance testing and in manufacturing. So what tests do we do as part of an electrical safety test for 60601? We do an earth bond test, and we do leakage tests under various single fault conditions. We do earth leakage, we do enclosure or touch leakage as it's otherwise known. We do patient leakage, measuring AC and DC currents. We measure patient auxiliary AC and DC leakage, and we measure patient F-type. Earth bond. So what are we measuring with earth bond? If this is our medical device, and these are our live conductors in and neutral, this is our protective earth. We want to make sure with the medical device, and this is our chassis of the medical device, if any conductive accessible parts have on a class 1 appliance, because earth bond is class 1 only, or class 1 equipment only, we want to make sure that any accessible parts that are metallic and conductive have a low path of resistance to the protective earth. These are your pass-fail thresholds as far as 60601 is concerned. So you have less than 0.1 or 0.1 is a good reading, excluding the power cord. If you're using the power cord, then 0.2 of the ohm is the acceptable pass-fail threshold. Earth leakage. We discussed earth leakage and what earth leakage is in part 1. I'll go further into detail in how it works with the medical device under test, which is here, and our Rigel device. The Rigel device in this picture is in blue. Everything in this schematic is internal to the Rigel device. And I'll explain this further in that when we're looking at earth leakage and we're looking at the flow of earth leakage within a medical device, we have to measure that, and it's measured via the safety analyzer. So what I will do in this presentation is I will talk through where the current flows from which point from A to B and how things are measured. So earth leakage is fairly a vital measurement. We're measuring any of the leakage from capacitive coupling on any of stray capacitance within the medical device. This is going to be a familiar drawing. We have this would be the chassis of the medical device. This is our live and our neutral, and this is our applied parts, which should be totally isolated from any of the or opto-isolated from any of the electronics or conductors from the mains in. So if I have any stray capacitance or dielectric resistance within the medical device, what is happening is we have 230 volts in on our live. Bear in mind these relays are our single fault conditions: normal supply, open neutral, reversed. We have 2 relays at reverse, and then we have reversed supply open neutral. So we have internally within the Rigel, we adhere to 60601 with a number of opening a number of relays in a sequential manner to provide the single fault conditions. So if I was to have mains input 230 volts coming in on your live, the current would flow through the live conductor and it would flow to the neutral conductor to provide a functional amount of current for the medical device to operate as its intended purpose of use, as the manufacturer wanted the device to be powered. So that power consumption, let's say if we have the total system is 100 milliamps. Well, let's say we have 99 milliamps flowing between live and neutral to power the device to make sure that it operates. It can do its diagnostic work or whatever the patient, the medical device requires. Well, if the system is 100 milliamps and the current consumption or functional current is 99, then 1 milliamp must go missing in the system. That 1 milliamp that goes missing in the system is what we call non-functional current and what we call leakage current. So how does this happen? So we have the current consumption to power the device. Well, inside the medical device, there's lots of stray capacitance, there's lots of dielectric resistance, and somehow it makes its way back through all the stray capacitance back through to the protective earth, and we measure it through our 1K body model back to the protective earth. So we have the live conductor coming in, all this stray capacitance, and then eventually it should find its way back to Earth, and it gets measured internally within the safety analyzer or the Rigel, and gets converted. We measure voltage. This is your body model, and then that gets converted to current. And here are your pass-fail thresholds as far as current is concerned. Enclosure or touch leakage, similar to earth leakage, applicable to class 1 and class 2. We select or we have a number of single fault conditions, 6 in total. So rather than the current flowing directly through the earth via the body model, what the touch current does is any exposed metalwork or conductive parts on your medical device will be measured through the body model and back to the protective earth. So effectively, what we're trying to simulate here is if the earth goes missing in a single fault condition of a medical device, then any earth leakage, if you were to touch a conductive or metallic part of a device, then this would be the equivalent current that would flow through you or a human back down to protective earth. So if we had 230 volts and we had our system, let's say, and I'll use the same throughout the presentation, let's say the system current consumption is 100 milliamps, we have 99 milliamps flowing between live and neutral. Well, 1 milliamp is in the system somewhere, escaping through stray capacitance and dielectric resistance. If we open the earth, which is one of the single fault conditions, then the leakage will flow through the body model back to protective earth. So effectively what we're simulating is an operator or a means of operator protection to clarify how much current would flow through a person if they were to touch a metallic chassis or an accessible conductive part if the protective earth was open. And here are our pass-fail limits. The pass-fail limits of 60601 there is a correlation between that and the physiological effects of current, which I discussed in the first part of our presentation. Patient leakage tests. So we've discussed earth leakage and we've discussed enclosure leakage. Patient leakage test is the amount of current that will flow from an applied part through our body model to the protective earth. So within a medical device, we should have total isolation between our applied parts and any conductors that carry current. So if we have 100 milliamps flowing in the full system, and we have 99 milliamps flowing in between live and neutral to power the device, 1 milliamp is getting lost in the system through stray capacitance and dielectric resistance, and the power of the electronics that provide the diagnostic measurements and whatever the applied part is doing to as if it's the definition of a medical device for its intended purpose of use. That we are measuring the current that flows through. That we are measuring the current that flows from a single applied part through the body model. Remember, the blue here is internal to the Rigel. Measured through our 1K body model back to protective earth. So we are measuring any stray capacitance, any current that could be passing through any stray capacitance or dielectric resistance from your applied part back to protective earth. Again, this would be in a situation, the patient could be on the hospital bed, and if he is in contact with protective earth, that would be the equivalent leakage that would flow through the patient. Clearly, we don't want, especially for CF, so we don't want any current flowing. So we have very, very stringent low levels for CF and DC as far as single fault condition is concerned and normal condition. B and BF patient connections are tested by shorting all the patient connectors together, but CF patient connections are measured separately. That's something to bear in mind. Patient auxiliary leakage test is where we're measuring the leakage between applied parts. So we're not measuring to protective earth. If you have an ECG or another device that has multiple applied parts, patient connectors, what the Rigel device is doing is it's measuring any current that may flow between the applied parts via the 1K body model. It has the same pass-fail thresholds as patient leakage. An individual patient connection is tested to all the other patient connectors combined, something to bear in mind. This is done internally within the Rigel 288. All of the patient connections will be satisfied as per 60601. Patient F-type leakage, or otherwise known as mains on applied part. What we want to check, what we want to satisfy with 60601 design is that I've discussed earlier that applied part, we want total isolation here. So we've got conductors coming in that power the device to make sure the device operates in its intended purpose of use. What we want to prove is that if any mains or any voltage can become present on the patient that will be connected to an applied part, we have total isolation so it doesn't flow back to protective earth. Within how we do this, within the just a reminder, in the blue area is the Rigel device. We provide isolated voltage, 110 volts of mains voltage. It's isolated, which is another factor to be aware of. It's also current limited, so it might put out skilled mains voltage, but it's current limited, so it won't provide power to any device. And this is internal to the Rigel, so it's both referenced to protective earth. So if we put 153 volts out, this would be at 230 volts. Through the current limiting resistor, through our body model, and we put this mains voltage on each of the applied parts, we will measure any current that will pass back to protective earth. So that's what we're measuring here. For both BF and CF, bear in mind you wouldn't measure mains on applied part for a type B It's only B, F, and CF. The reason why: B is earth referenced. If you put mains on anything that is earth referenced, then you're just going to get an inrush of current. So for obvious reasons, we just check B, F, and CF. So I'll just go over that again. We put mains voltage, or 110 volts, 110%, mains voltage, via a current limiting resistor through the body model onto an applied pot. So we should have 253 volts at this point, and we want to prove total isolation between these applied parts, so we can say that no current is flowing back to protective earth. And then again, we have a number of relays that open to satisfy the single fault conditions. Those are our pass-fail limits for BF and CF. BF, all patient connections are shorted together within the applied part. Again, the Rigel does this for you. For CF, all patient connections are measured separately within the applied part. And here are our pass-fail thresholds for 60601 3rd edition. I'll just leave that on the screen there for you chaps to take in for a couple of seconds. That was 60601. Now we're going to talk briefly about 62353. 62353 is recurrent test and test after repair of a medical device. Published 10 years ago, or 11 years ago now. The second revision came out in October 2014, and it's well accepted and used in most of Europe by leading manufacturers and hospitals, but it's been adopted in other areas of the world too. Provides a quick and uncompromised test on electrical safety of medical devices, part of the planned preventative maintenance schedule. So what we have as part of the 62353 is a sequential number of tests. So the objective is to find, or at least to prevent, potential faults. And we have a visual inspection. We have testing protective means, which is earth bonding and insulation. Insulation, by the way, is not mandatory. It's optional. Some manufacturers use insulation, some don't. You would have to refer to service manuals for that information. And then we have leakage current testing. We have 3 different methods of measuring leakage, and I'll go into that into depth over the next couple of minutes. We have the testing of the performance of a device, and we also have reporting and analysis that could lead to protection. So this is your sequential order of your PPM, where we would have a visual test, we do a protective earth resistance, we do a leakage current. We could optionally do insulation resistance test. We do a functional test, which actually measures the functional current of the device. This is a power reading, how much wattage your medical device actually draws to operate. Then we have the reporting of the results, and we have the evaluation of the results. And that's something that we'll go into later. The visual check. What do you look at for a visual check? You want to make sure that the enclosure is including contamination or decontamination of the medical device is good. We want to make sure that any electrical connections, power supply, applied parts all look good. Does it have the appropriate fuse rating? Very important. If you have a medical device that should have a 3 amp fuse, and the fuse rating is actually, the fuse that is in the device is much higher, 10 amp, 13 amp, then it's it's an inappropriate fuse. Very important in electric safety. If there's too much current being drawn because the device is faulty, then you could damage the device, but you could start a fire, etc., etc. So looking at the fuse rating is very important for a medical device or any electrical device. We look at safety markings and labeling, class 1, class 2, BF, CF, etc. We look at the integrity of mechanical parts to make sure they function as per intended purpose of use. And one major thing really with the visual test, because it is the first test, is 70% of all faults are detected during the visual inspection. We don't want to plug in a medical device that doesn't look right, doesn't look correct. It's very important. This is why it is the first test in the sequential order of 62353. Earthbound currents, a little bit of a, not so much a myth, but 60601 uses 25 amps, which is effectively a stress test. And this is part of a manufacturer's conformance test, almost like a type test. 62353 adopts 200 milliamps for in-service test. The trend for in-service testing is towards lower currents, and we went over that in the first part of the seminar. So if you want to remind yourself of those methodologies, watch the first part of the seminar where I go into depth between 25 amps and the benefits of using 200 milliamps. These are some of the characteristics that are further stipulated within the standard. Just to reiterate the points of earth bonding, notice that the pass-fail limit is slightly larger in 62353 than it is in 60601. Insulation test. What is an insulation test? It's not mandatory for 62353, but it's generally adopted in portable appliance testing in the UK and in end-of-line production testing with some of your high-pot testers that are used to validate electrical goods before they leave a factory. What happens is within the tester, the Rigel will short, live and neutral together. So we drop a relay. If this is our medical device here, we drop a relay across live and neutral together to short it. We apply either, and the Rigel 288 Plus and 62353 offer a number of ranges, anywhere between 50 volts to 500 volts DC. So between our protective earth and live and neutral common, we apply a large DC voltage of 500 volts DC, and we measure the resistance in megaohms. So it's a high resistance, and we have some of these pass-fail thresholds that the pass-fail thresholds in 62353 have been generally adopted from what you would call accepted levels of resistance. This is from both pad testing and from production testing. So this would be a general class 1, class 2. This is our applied parts. So this would be our means of operator protection. This would be our means of patient protection, where we're putting a large voltage between our applied parts and our protective earth, and we measure what the resistance is. So 62353 leakage tests. We have equipment leakage, which is input safety, means of operator protection. And then we have applied part leakage, output safety, which is means of patient protection. We use different methods of leakage tests, and I'll go through each one of those individually. We common patient connections, so slightly different to 6 or 601. we're measuring the total leakage of the system. And we're also comparing and analysing results. So, equipment leakage means of operator protection. Total sum of leakage deriving from the incoming mains to earth via applied parts and the enclosure. So if we have a look at this diagram over here, this is our medical device, our applied parts, our accessible conductive parts, even isolated parts that might be conductive, are all commoned together here. That's all done within the Rigel. And then we have the facility to open the protective earth. The measuring device, the 1K body model, is within this circuit. So if I was to measure any earth leakage, again, I'll use the same example. If the total system is 100 milliamps, 1 milliamp will go missing because of all the stray capacitance and dielectric resistance within our medical device. So if you have 99 flowing between live and neutral to provide power, 1 milliamp must go missing. Where does it go missing? It will flow through the combined connections through our measuring device, our 1K body model, back to protective earth. And that's what we're measuring. Applied patient leakage, means of patient protection. Total leakage of patient protections, AP and earth, non-conductive parts of the enclosure or chassis. Very similar to mains on applied part. It is the direct comparison to 60601 mains on applied part. So we put mains out from an isolated voltage within the Rigel onto the applied parts. Again, it's current limited, but the current limit is slightly less than 60601. And we're measuring the RMS value. So this is our isolated voltage, which is linked between our protective earth and our chassis. The measuring device is measuring any of the mains on applied part, and hopefully this should prove any isolation between our applied parts back to protective earth. So this is what we're proving. We're proving isolation if mains voltage were to fall on to our applied parts back to earth, because we don't want that. Similar thing with 60601 and 62353. The reason why you put mains on applied part, yes, it is to prove the isolation, but also it's to prove that whoever is under or has a patient connection on them, let's say a guy is lying in a bed, if he happened to come in contact with any hazardous voltage source or current source, then he should remain floating. So he should remain isolated because of this barrier that is internal within any medical device from protective earth. So that's the purpose of doing mains on applied part testing. It's not called mains on applied part testing within 62353, but effectively that's what we do. We put a potential in there that is isolated. So why do we have different methods? What is this confusion between our different leakage methods? Which one does what? How does it does it? Well, we'll go over that one by one. The direct method is the true leakage of earth through the measuring device, and the direct comparison is 60601. So the only difference between the 60601 is we common all of our applied parts to our chassis and our isolated parts on the measuring on the medical device. It is what you have to consider is that it is ground interrupted. So we open ground. It uses the 1K body model to measure the leakage. It is susceptible to secondary earth path and teraneutral systems. Now this is partly a flaw with 60601, in that in 60601 I went over in the first part of this series that testing secondary earth and testing medical devices that may have a secondary earth or may be on a teraneutral system can give false results. So that's something to bear in mind if you're going to choose the direct method. It has the same idiosyncrasies as 60601 is concerned. Differential method. The differential method is not susceptible to secondary earth and is not susceptible to, well, it has the, it is the total leakage of a system, because we're not measuring through the 1K body model. Every other test that measures leakage, 60601, 62353, we're always measuring through a 1K body model. So 1K will be in series of the circuit. If 1K is in series all this time, when measuring, just like any current shunt, it's not the true leakage measurement. There's impedance there. Something to consider when you think about measuring leakage current. So how do we measure differential leakage? We measure it by, if we have, again, I'll use the same example, 100 milliamps in the total system. If I have 100 milliamps flowing between live or through live, and I have 99 milliamps flowing through neutral, then 1 milliamp must be missing. And that is assumed that it is going to flow through our protective earth. So I'll just reiterate that again. We have the full system is 100 milliamps. What we detect is we detect the difference of current that flows through our live conductor and flows through our neutral conductor. And then the assumption is the missing current through stray capacitance or dielectric resistance flows through our protective earth. So this is why we can test on secondary earth conditions and connections within a healthcare environment. There are some considerations in that anything under 100 microamps is relatively hard to measure. It is susceptible to external magnetic fields, because what we have in this system here, the measuring device, is actually a current transformer. So it is measuring, and it could be susceptible to, because of the nature of a current measuring device, like a current transformer, it can be susceptible to magnetic fields. Also, if you have a high current that is flowing between live and neutral, if you have 13 amps flowing, then if you're looking for 1 milliamp and 13 amps is flowing in this system too, it can be quite tricky to measure the correct earth leakage. Limited current response, because the current, just like any transformer, we're looking at frequency, or we're looking at the change in current as far as frequency is concerned. So it's AC only, no DC currents will be measured. The alternative method, similar to an insulation test, a DC insulation test, but we're using AC. So we're using, or at least we're simulating dielectric strength tests, but using only mains voltage. So we short live and neutral together on the input of the conductors that power the device, and then we apply an isolated voltage at mains potential between all of these connections coming together. So that's the protective earth. This is our enclosure or chassis, any conductive parts, and our applied parts. So we don't power the medical device. It doesn't get powered at any time. We're just testing between the conductives with live and neutral shorted to our important return points to try and ascertain and to measure any leakage via our 1K body model measuring device. How is this beneficial? Because we're not measuring, we're not powering the device. So I mean, you would ask why. What's the benefit in using the alternative method? The alternative method has a big bonus point in that we can test on systems that might not have enough IT system. So if it's a non-terra neutral system, which I talked about in our first presentation, it doesn't matter. We can test on any systems. It's not the results of measuring the leakage will not be affected by a terra neutral system and will not be affected by any secondary earth. It does have some considerations in that we use a current limiting resistor. This current limiting resistor means that the actual readings are scaled, and we use a scaling factor to ascertain what the correct leakage current would be. The equipment isn't activated, it isn't powered at any time. Slight drawback in that you're not going to power any of the applied parts. The applied parts will be unpowered. Therefore, will there be any leakage present if you're not powering them? Highly unlikely. And it's only really directly comparable with the 60601 open neutral. And we'll look at that. We'll look at the comparisons in the next couple of slides. Here are the pass-fail thresholds for 62353. You'll notice that they're very different from our 60601. So we're going to have a look at what are the differences between using 62353 and using 601. Where are the benefits? What's the difference? Why is it applicable? Well, your 60601 is very much like our type test. It's very much like our crash test dummy. It is used in the design phase and at the end of line in a production environment. But when we take in our car to a service, we want to use in-service testing, which is the 62353. So that there's clear difference between a type test, which is stress testing in the R&D phase to make sure that it is going to be good for creepage of leakage and high voltages. When we do our 62353, it's designed for clinical engineers in hospitals and maintenance. There's a clear definition between the two. As far as I'm concerned, my role within Rigel is to educate guys around the world to get rid of 60601 testing and adopt 62353, because adopting 62353 has been totally designed. The purpose of the standard is for preventative maintenance measures. That's how we should be using 62353. 60601 is for the R&D guys, the manufacturers. 62353 is for the clinical engineers, the biomeds that want to make sure medical devices are safe to use in a healthcare environment. So you've got the set data. I'll just reiterate that again. 60601 R&D, type testing, production working environments, acceptance testing. There is crossover here. You can use 62353 for end-of-line production and for acceptance testing, but more importantly, the standard is designed for our preventative maintenance and repair maintenance of a medical device. Very clear. I must reiterate those points. Where is the comparison? 60601, we have earth leakage. earth leakage is either differential or direct. That's like for like. Earth leakage, single fault condition open neutral is 60601, is our equipment leakage alternative. Enclosure leakage, single fault condition earth is our equipment leakage, both the same there, you'll notice. Patient leakage is equipment leakage in that the enclosure probe is disconnected, and we have the return path is via some of our applied parts. Then we put mains and applied parts as far as 60601 is concerned. The direct comparison is applied part leakage as far as 62353 is concerned. The 60601 is all using the 1K body model. Some of the 62353 use scaled and factored calculations to get the correct measured leakage. The 60601 uses the direct method only. 62353 has 3 different types of ascertaining and measuring hazardous currents. So if I was to test the same medical device, what would my results look like? Well, this is our 60601 results here on a device, and this is our 62353 results on a device. There's our earth leakage, there's our direct leakage, same result. There's our reversed earth leakage, there's our reversed direct leakage. There's our neutral open, both reversed and in a normal condition, and this is our equipment leakage alternative. So that's how we can draw to the conclusion, both with leakage, earth leakage and enclosure leakage, the direct comparison between 60601 and 62353. The big selling point really is time. If you have a hospital with 1,000 beds, then you're going to have a lot, and I mean a lot, of medical devices. So your department that tests medical devices, time is critical. How you employ your staff, how your staff is allocated their work. If you're using 60601 to do your safety testing, as opposed to 62353, well, if I was to do a class 1 instrument with 10 applied parts, if the applied part was type CF, let's say for instance an ECG monitor, 60601 would require a total of 290 tests would be performed. That's going to take a lot of time to go through one test. 62353 does 4. I could do a factor of probably within a day, maybe 50 times the testing with 62353 as opposed to 60601. That's something to bear in mind when the whole purpose of the standard really is to make as far as 62353 is concerned, is to make the clinical engineer or biomedical engineer's life a lot easier. Here's another example, class 1, if we have 5 CF, 2 BF, like a defib tester, for instance. We've got 190 tests. If we use the 60601 standard, we have 6 tests. If we use the 62353, clearly there's a big benefit as far as time is concerned. And this is why at Rigel we really promote 62353. So we have, just to summarize, we have input and output safety in regards to means of operator protection and means of patient protection. It gives alternative methods for typical problems, so you can use a differential leakage where the secondary earth path isn't applicable. We have fewer results, meaning more time to fault find and analyze medical devices. Remember, preventative maintenance is not about passing as many items as possible, but preventing problems before they might occur. A big part of the standard is to analyze leakage tests and do not accept pass on face value. Right, so those are the two main standards for testing the electrical safety of a medical device. 60601, type testing, R&D, but can be used as a service test. 62353, very much service testing. 61010 is for laboratory equipment. Safety requirements for electrical equipment for measurement control in laboratory use, not medical devices. What is the definition of a medical device? A medical device is electrical equipment designed for treatment, monitoring, and diagnosis of patients, powered from not more than one connection to mains supply, in which are necessarily in physical and electrical contact with the patient, or transfers energy to or from the patient, or detects such energy transfers to or from the patient. So basically anything that is used to monitor or diagnose patient is a medical device. Lab equipment, as far as 61010 is concerned, is not a medical device. Although medical devices can be still type tested to 61010 adherence, that is important. So it can be part of the process of a medical device. Let's not ignore that. The standard itself describes testing requirements during design and the production phase of a medical device or any electrical device. Production line testing, not so much routine testing, where you would use high pot testing, which is high potential, and earth bond. No maintenance or annual testing is described in the standard. So electrical safety, well, it's not really typically specified in 61010. Leakage measurements are only required if measured touch voltage is greater than 33 volts. However, touch current is ultimately a safety indicator. So if we, over in the UK, we would use, and in Europe, and possibly parts of the US and Australia, that we'd use portable appliance testing to measure 61010. But you can, with the Rigel device, the 288, you can measure 61010 and test laboratory equipment just by extrapolating or manipulating the figures. So we can use touch leakage. If we have touch leakage of 100 micrograms, that is equal to 100 millivolts touch voltage. So on the Rigel medical website, we have an application note that tells the customer how to use 61010 safety testing of their laboratory equipment with the Rigel 288 device. Go to the website, you'll be able to find that app note there. Very useful. So the testing which we stipulate at Rigel, and which is part of a general safety test, there's no current within 61010. There's nothing specified to stipulate bond testing, but we give 0.2 because that's generally accepted across a lot of pot testing and the experience that we have as manufacturers. And then we have normal condition and single fault condition, both touch leakage and touch voltage thresholds. We use or I should say that the 61010 uses a different body model to what the medical body model uses in 60601. So the frequency response is less sensitive to that of a medical body model. Right, that is the end of the presentation. If you have any questions, please email it on that email address. I'd like to bring our partner in at this moment in time, if he's available. Dinesh. Dinesh, are you there to give an overview?
Yes, Michael, I'm available.
Yes. Is there anything that you want to discuss?
Yes, see, thanks for your session. Anyway, it is very much detailed regarding the different standards of medical devices. Yes, I have few queries with which I'll just send you a mail to your mail ID so that I'll get it clarified and explain to my customers in India. And anyway, thanks for the viewers who has come into this particular session and watched this presentation on IEC standards. And I hope, Michael, you are sharing this particular presentation to all the attendees.
Yes, yes. The video will be shared.
Okay.
Yeah.
Yeah, and many of the customers have sent their messages saying that the time is not feasible for them, but they requested for this presentation to be sent to them so that by going through this, they will get the knowledge. And I hope many of the people, even though they are not live in the sessions, they wanted to see this particular whenever they are getting the time. So anyway, it's a eye-opening session, and looking forward for the part 3. So let's see that how we can utilize this particular into 288 plus. But I like to know that is there any specific 61010 devices available which you mentioned apart from pad testing? Dedicated 61010 testing tool for laboratory products?
Well, we do. Rigel actually makes what we call the Safe Test 60, and the Safe Test 60 has it has different body models to suit the correct testing for 61010 and 60601 and some of the 62353, I believe. So yes, the Rigel Safe Test is specifically designed for 61010 in laboratory equipment. It doesn't have any applied parts.
Okay.
So
can you
yeah, you were going to say? Sorry.
Yeah, can you just tell me in R288 plus electrical safety analyzer, when we are performing earthbound test currently, because when we go for this earthbound test, there is no provision of selecting whether it belongs to 60601 or 62353. We are just selecting earthbound as a test actually, correct, no?
Yes, that's correct. The only thing that would...
But in 288 plus,
yes.
What is the current is applied actually, because we don't have any control of changing the current from 200 milliamps or 25 amps or 1 amps.
Well,
but what is the current applied in 288 plus for earthbound test?
Well, what you have, and which is applicable in the first part of the series of what I discussed in depth, is that with the 62353 and the 60601, what the Rigel does is there's no selection of different currents, but what it does, it sends out a spike called the zap circuit. So that's the equivalent of 25 amps, but only for approximately 1 millisecond. And then it dies down exponentially to 200 milliamps. So it covers, the Rigel to it doesn't put out a constant 25 amps as per 60601, but it can still be used for 60601 testing as far as service is concerned. I mean, it's generally accepted these days as far as, and I discussed it in the first part of this series, that using low current is much more beneficial than using high current, because to use high current, to use 25 amps, it's a stress test. It should only really be done in the design and R&D phase of any device. It doesn't need to necessarily be a medical device. Any electrical device we use high currents just to stress test, just to make sure that in its design phase, it can go through rigorous type testing. So in service testing, we don't want to be stress testing a device over and over and over, because if you stress test a device using high currents, because 25 amps is a high amount of current, then you've got potential to damage the device. This is why service testing and maintenance testing use lower currents for earth bond. One of the main differences, one of the main differences, what does change actually, is the pass-fail threshold. You've got a slightly larger pass-fail threshold for 62353, 300 milliamps and milliohms, whereas 60601 is 200 milliohms.
Okay. So one more thing, in insulation resistance test, even though it is optional,
Yes.
we tend to do it here. We are getting a reading saying that it is more than 100 mega ohm.
Yeah.
So always it shows 100 mega ohm, but the limit says that more than 70 mega ohm. But if it's showing more than 100 mega ohm, means it is good in insulation only, we have to consider, correct, no?
Yeah, that's correct. That is correct, yes. You've got some pass-fail thresholds at 70 mega ohms. 100 mega ohms is basically saying that it's beyond its open circuit, it's infinity, because we only have a certain measuring range within the Rigel. Even though we're putting out a large voltage, we have to we have to define what is infinity. And 100 mega ohms is deemed to be a pretty large amount of resistance. So that's the reason why you could get a reading of 100 mega ohms.
Okay, thank you.
Right. Well, I think if any of this is going to go out to the people that registered and the rest of the people that we have on our emailing list. So the video should be good, hopefully. If you want to share it amongst your friends or colleagues, then that might be a good idea. And then we'll have the third part of the series. The third part of the series is going to concentrate, it's pretty much in-depth like we have in the standards, but more on practical testing. How we test with a three-phase or fixed appliances, how we test with ultrasound devices, using our Rigel 288 Plus. So that's something to bear in mind. That might be of interest to people.
Yeah, that should be fine. Yes, people will be looking more on this practical now then. So we'll try to spread this particular to maximum the people. And anyway, the attendees whoever registered for this program will have this presentation sent so that they can verify at any time, and they can also share with their subordinates, and they will see like how things going on.
Right, perfect. Well, thank you very much to the attendees, and thank you very much, Dinesh, for being the great help and being the panelist on this presentation. Thank you.
Thank you so much. Yeah.
Right.
Bye.
Bye. Bye.